Yeah, so again, I'm just using this PowerPoint here in my video for my own reference. I'll post this PowerPoint on Blackboard for you to follow for this little video. And in this video, I'm gonna talk about cylinder head, valve train components, and gear train of the engine. So if you want to follow along with the PowerPoint, like I said, I've posted it on Blackboard. So just follow along. I'm not going to hit every slide of this PowerPoint. Again, we're trying to condense a lot of information down into these short few lectures. So the first place I'm going to start is the gear train, because that's ultimately what drives our valve train in the cylinder head, as well as a lot of other accessories for the engine. The valve or the gear train of the engine can be located in the front or back of the engine. And ultimately, the gear train is a way to distribute the rotational force created by the crankshaft. So ultimately, we're using the crankshaft to drive our camshaft. In a lot of engines, we use it to drive a fuel pump, we use it to drive a water pump, etc. Air compressors, just about anything you can think of that uses mechanical rotation to do work, we could drive off the engine gear train. But our primary focus today is talking about our valve train. So, like I mentioned, our gear train drives the camshaft. And as we talked about in our in-person lecture, and also looked at the camshaft is what gives us the motion that actuates the intake and exhaust valves, as well as fuel injectors. Not all engines use the camshaft to operate the fuel injectors, but certainly a lot of diesel engines use the camshaft to drive the injectors. Like I mentioned in the in-person lecture, if we are using the camshaft to operate our fuel injectors, that type of fuel system is called a unit injector. The fuel injector, is making its own high pressure for the injection of fuel into the cylinder. The gear train also is where we will time the engine. And if you don't recall, when we refer to timing the engine, we are talking about making sure that the intake valves, the exhaust valves, and the fuel injectors open and close and fire at the right time in relation to the piston in its travel. So we want the intake valve to open when the piston's on its way down. We want the exhaust valve to open when the piston's on its way up. We want the injector to fire near top dead center of the after the compression stroke. Let's get to my next illustration here. The next slide I'm looking at is our camshaft terminology slide that you can reference from the PowerPoint I posted. But this just shows us the side profile of the camshaft and the specific geometry of the camshaft that gets us the reciprocating motion that we need to open and close the intake and exhaust valves. So if we look at this illustration, we've got the general geometry of a cam lobe. That cam lobe, ultimately, as it rotates, the outer surface of that cam lobe gets closer or further away from its center axis of rotation. When we incorporate that cam lobe into the rest of the valve train, we can use it to get that linear movement that we need for the valves. Some major parts of that camshaft lobe geometry is the base circle, and if you can see here, me pointing to this illustration, the base circle is the part of the camshaft lobe where our valve would be closed. Or if we're talking about the injector, it's when the injector is not being fired. The next part of the cam lobe geometry that is quite important is the nose, or the ascent or descent ramp. And that's where we're going to get our linear movement for the opening and closing of the valve. I'm going to jump forward a little bit and look at our full camshaft geometry, or camshaft and valve train geometry. The example that I'm using from the PowerPoint is the slide that is labeled roller cam follower actuated valve train. I referred to this style valve train in our in-person lecture as a push rod style valve train, in that our camshaft is down located in the engine block, and then we have a push rod that transmits that reciprocating motion up to the top end of the engine in the cylinder head. And the major components there ultimately is the rocker arm, camshaft obviously, push rod, and the cam follower. Ultimately, the cam follower is the component that directly interfaces with the cam lobe, usually has a roller on it, and that roller is what comes in contact with our cam lobe. And as our cam rotates, that cam follower rides on that cam lobe. And as the nose of that cam lobe rolls around, it pushes up on our push rod, which transmits that linear movement to our rocker arm. And the primary job of the rocker arm is to take that upward travel of the push rod, and the rocker arm's kind of like a seesaw, but kind of different than a seesaw. On one side of the seesaw, we're pushing up on the bottom side of the seat of the seesaw, and on the other side of the seesaw, we're using the bottom side of the seat to push down on the valves. And when we push down on the valves, that opens the valves. And again, we briefly talked about this in our in-person lecture. Ultimately, the rocker arm, camshaft, cam follower, all those components are responsible for making the valve open. Once we're back to the base circle of the camshaft and we're not pushing up on that rocker arm anymore, springs are what makes those valves close again. And those springs are attached to the valves up in the cylinder head. So when that rocker arm is no longer pushing down on those valves to make them open, those springs pull the valves back up and make them seal against their port. All of these parts in the valve train are there's a lot of parts that are in contact with one another, and our lube oil from the last lecture is crucial for this for these components to last any amount of time. So we have lube oil fed to all these components in the valvetrain. There's not too many engines today in service that are a pushrod design anymore. In modern engines, we've gotten rid of the pushrod because, like I mentioned in the in-person lecture, we took that camshaft and we moved it from the engine block up to the cylinder head, and that's what we refer to as overhead cam. By moving that camshaft up into the cylinder head, we get rid of that pushrod, and now our cam lobe is able to act directly upon the rocker arm. And we also have some kind of cam follower in there between the rocker arm and cam to transmit that movement. But nonetheless, whether it is a pushrod style valve train or an overhead camshaft style valve train, all of the operational principles still apply. I don't know if you guys got to the point with Joseph when you all were here in the shop of doing lash adjustments. We talked about that briefly when you were with me, and that is making space between all these parts so that when everything gets hot and all our components expand from that heat, we call that thermal expansion. We adjust that lash or that free play between all these parts so we don't hang open the valves when the cam is on the base circle. When the cam is on its base circle, the valves absolutely have to be closed. If the valves aren't closed, we can't make compression. If we can't trap that intake air into the cylinder when that piston comes up on its compression stroke, we don't have a compression stroke. So we need to make sure that there is enough valve lash or clearance or play between these parts so that when everything gets to operating temperature, our valves are still able to close fully. There's a slide, and again, you all can look through these slides yourself and pick out. There's a lot of useful information that we just don't have the time to lecture on absolutely every little detail. But some bullet points here that are important to look out for is anywhere where all those parts come in contact with one another. Again, there should be oil, or there should be lube oil between all these components. And ultimately, the only time that any of these valve train components should be in contact with one another is during startup, where the engine has been sitting and there's no oil pressure from the lube oil pump, and that oil has, by gravity, drained back down to the oil sump. And when we go to start up the engine, it takes a moment for our lube oil pump to pressurize our lube oil galleries and get oil distributed to all these moving parts. So briefly, on startup is where we're going to get this wear between our rocker arms and valves, between our camshaft lobe and the cam followers. All these places are things that we should be looking at and inspecting and making sure there's no surface damage to the cam lobe, the valve stems, any of these parts. Usually, if we do have damage from misadjusted components or lack of lube oil, it's pretty obvious when there's damage to these parts. whether it be through heat or friction or both. The damage is going to be rather obvious. Usually when we're looking at machined surfaces like this that are move, there shouldn't be any wear patterns that you can catch with a fingernail. If we were to inspect a camshaft and are looking at the cam lobes, I don't know how well you guys can see this camshaft I've got here, but there shouldn't be anything on these surfaces that can catch your fingernail. If there is, then that surface is excessively worn, and that problem needs to be addressed rather quickly. It's going to hurt engine performance, especially if we have wear on a cam lobe. Ultimately, if the wear is bad enough, the amount that our valves are opening is going to be affected. If we take surface material away from our cam lobe, ultimately, it's going to affect how much travel we get from that cam lobe. Some points they point out on our inspection. This is referring to a pushrod style valve train, and they're just calling out all those points of contact. And I encourage you to look through these slides and get what you can out of them. Talking about bent push rods. Again, I don't know how much you all will encounter a push rod style engine, but a common failure mode with a push rod style valve train is those push rods to get bent. Just to kind of reiterate some things here, we're talking about the rocker arms in this slide. The rocker arms are just levers, which is not a relation that I made originally, but it's just a lever. On one side of the lever, our cam lobe is pushing on that lever, and on the other side of that lever, we're pushing on the valves to make them open. The rocker arms transfer camshaft motion to the valves and mechanically actuated injectors. They're used in both in-block camshafts and overhead camshaft configurations. So whether it's a pushrod style engine or an overhead cam style engine, we're still going to have rocker arms. And the rocker arms, again, are where we're going to find that adjustment to adjust our lash to account for our thermal expansion. You guys may also remember from our in-person lecture, we talked about that thermal expansion and drew the relationship between the heat and the amount of valve lash specification that we have, in that the exhaust valve rocker should have more lash than an intake valve rocker arm, because the exhaust rocker arms are exposed to more heat. More heat means more expansion, means that we need more space for those parts to expand without hanging the valves open. And our next slide, labeled the rocker arms in the PowerPoint, shows some up-close views of the valve train. In one, we have an electronic injector on the left. In the example on the right, we can see our rocker arms. They have a roller where they interact with the camshaft. So instead of any kind of cam follower, like we looked at in the pushrod engine, instead on this overhead camshaft design, the rocker arm itself has a roller that comes in contact with our camshaft lobe. So the roller also helps with the friction between those parts. We still have lube oil there, but the roller just reduces friction between the camshaft and the rocker arm. Most of the engines we see are a single camshaft. There are some examples of engines that use two camshafts, but we can usually get the job done with one camshaft. Even if we have two intake and two exhaust valves per cylinder, obviously I'm talking about a 4-stroke engine, we can use one cam lobe to actuate two valves. And the way we do that is through a valve bridge. And that is the component that stretches across between two valves. You can see it in this illustration here on the PowerPoint slide. You can see our two valve springs, and right on top of those two valve springs, we can see the rocker bridge or the valve bridge. And ultimately, that is a component that goes between the two intake or exhaust valves that allows us to use one rocker arm to push and actuate two valves. And sometimes we have adjustments on those valve bridges, similar to the lash adjustment we do on the rocker arm itself. In some engines, you will see an adjustment that can be made on that valve bridge. Ultimately, our next slide talks about the cylinder head itself and the architecture or geometry involved with the cylinder head itself. Ultimately, our intake valves and our exhaust valves are a means of opening and closing ports that go to the outside air. Whether it's the intake or the exhaust valve, ultimately, the valves are connecting our cylinder, the inside of the cylinder, with outside air. If it's the intake valves, it is a means to open a port to let fresh air into the cylinder. And if it's our exhaust valves, obviously it's so that when we open our exhaust valves, it connects us to a port through the cylinder head that gets our burnt fuel and air out to the ambient air. Cylinder head valves provide the means of admitting air into and discharging exhaust out of the engine cylinders. The location of the valves, the lift, and the valve timing can influence cylinder gas dynamics. So all these things affect how efficiently we get air in and out of the cylinder. If we change the shape of the cam lobe itself, we can change how air flows in and out of that cylinder. If I go back to our illustration of a cam lobe, it's one of the first few slides in the PowerPoint. Instead of the nose of that cam lobe being real sharp and pointy, if we were to kind of spread that out and make it more rounded, that could increase the amount of time the valve is open versus how far the valve opens. So the difference between our base circle geometry of the cam lobe versus the outer circle, meaning the nose of the cam lobe, the difference between the two is the valve lift, how far the valve is being opened by that cam lobe. So all the way back at the cam is where we control how long our intake and exhaust valves are open and how far they open, which greatly affects how much air we get in and out of the cylinder. Next slide I want to look at is showing us the valve itself removed from the cylinder head without the valve spring or any of the other hardware that locates that valve within the cylinder head. And you can see here kind of the basic geometry of a intake or an exhaust valve. The main parts I want to focus on here is the two ends. The head end is the valve itself. That's where we're going to open and close, and that is the end of the valve that actually needs to seal when the valve closes. And the part of the valve that kind of is, it's all important, but the seat area, it's a hardened surface, but that seat area is cut at an angle, and that particular part of this valve is what actually comes in contact with the valve seat. The valve seat is ultimately the port in the cylinder head. That is where that valve needs to seal to the cylinder head and make trap air in the cylinder. That's also where the valve can get rid of heat. Any components that are exposed directly to the combustion chamber are going to get hot, and we have to get that heat out. And the way the valves get rid of that heat is through that seat area. So if that valve isn't making good contact with the seat, we can have that valve coming in contact and making a seal and still not making very much contact. Ultimately, you want as much contact to that valve seat as you can get, because that's where that valve is going to get rid of its heat. And where's that heat going? It's going from the valve into the seat of the cylinder head, and then ultimately the cylinder head's then transmitting that heat to our cooling system and getting it out. The other thing I want to point out on this valve diagram from the PowerPoint is the opposite end. We have some labels out here. We have some grooves in the top of this valve, and they're labeled keeper grooves. And that's ultimately how we retain the valve to the valve spring on the top side, so that when the rocker arm is done pushing down on the valve and opening the valve, when that valve needs to close, ultimately that spring needs to have a grip on that valve. Those keeper grooves are where that spring is gripping onto that valve. There's another illustration showing the valve in situ, the valve within the cylinder head, and kind of gives us some generic measurements of how that valve should fit into the cylinder head port. And ultimately what this illustration is not showing is our valve springs up on top, or any of the other components up there up top that attaches that valve spring to the valve itself. But you can kind of see here, we'd have our cooling water passages somewhere in the cylinder head around these valves. In this illustration, you can see they have highlighted in blue. That's the actual port that connects the cylinder to the outside air when the valve's open, of course. I'll briefly kind of talk a little bit more about the valve lash adjustments. I trust that Joseph did a valve lash adjustment with you all that were in the class, but I'll kind of touch on it a little bit here. There's a lot of different methods to adjusting lash depending on the engine. With the EMD style engine that we looked at out in the shop, there's actual special tools called go and no-go gauges that are used to measure the play between the rocker arm and the valve. But when valves are properly adjusted, there should be clearance between the pallet end of the rocker arm and the top of the valve stem. Valve lash is required because as the moving parts heat up, they expand, and if clearance were not factored in somewhere in the valve train, the valves would remain constantly open by the time an engine reached operating temperature. So like I said, we're not going to hit every one of these slides, but there's a lot of good material in these PowerPoints that I encourage you to look over. The up-close look at our rocker arm and how it interacts with a valve bridge and ultimately the valves themselves. We can see our valve springs, the valve stem with our retainer grooves, and you can actually kind of see the retainers in there that are trapping that valve within that spring. So be sure to look at all these illustrations that I've given you in the PowerPoint and try to get your head around them as much as possible. I encourage you to ask any questions on Blackboard. You can message me through Blackboard. I believe there's a discussion page on our Blackboard where we can kind of have group discussions. If there's any questions about any of this, I would love to answer them for you. I will say that we looked at these illustrations of a rocker arm in relation to our intake and exhaust valves. It's very similar if we have a unit injector. This is very similar geometry to how we actuate the plungers on the fuel injectors. All the same procedures are required when adjusting our rocker arms in relation to our fuel injectors. And it's kind of at the end of the PowerPoint here, we have like a summary, so we can kind of go through these bullet points and kind of make sure that I always use chapter summaries out of any textbook literature or any beginning of the chapter points to look for, just to check my knowledge and make sure that we kind of hit everything. Chapter summaries are a really good resource for studying. So I'm going to kind of briefly go over these little bullet points of the summary here. And again, spend as much time as you can possibly spend going over this material. And look at it multiple times. You pick up little tidbits of information or understand it a little better each time you expose yourself to the knowledge and information. The engine feedback components incorporate the engine timing gear train, the camshaft, valve and unit injector trains, and in some cases the injection pumping apparatus, so fuel pump. For purposes of study, the actuation mechanisms of the fuel injection components are examined in the sections dealing with specific fuel systems. So again, it's been hard to kind of condense diesel engines down into 2 days worth of lecture time. So I'm really struggle to pick out the most important things to cover with you all. Camshaft drive gears must be precisely timed to the crankshaft. Obviously, if we don't have the camshaft timed correctly with the crankshaft, our intake valves, our exhaust valves, our injectors are not going to do their job at the right time in relation to where the piston is in the cylinder. The camshaft gear, the gear that is on the end of the camshaft that drives the camshaft, you're either going to have a keyway that locks that gear to the camshaft, because you don't want the gear to move, or you don't want the gear to rotate and the camshaft not rotate. So you want to make sure those are locked together. We can either have an interference fit. Interference fit meaning that the hole in the gear is smaller than the camshaft, and you have to press them together, and that ensures that they don't rotate independently of one another. So wherever we position that camshaft gear in relation to the crank, it's going to stay there. Camshaft gears are not heat treated, but when they are fitted to camshafts, let's see here, let me restart. Camshaft gears are heat treated when they are fitted to the camshaft. So it is essential that they be heated evenly to a precise temperature for fitting. And that's if it is an interference fit. Sometimes you can heat up that cam gear to get that center hole to expand so that we can put the camshaft in the cam gear and they be clocked properly. Camshafts may rotate either with or opposite to the direction of the engine rotation. Camshafts, gear trains may use spur cut gears or helical cut gears. I encourage you to look more into the different types of gears that are used in any of these subjects. Helical or spur cut gears can be used in diesel engines. Thrust loads are much higher when using helical gears. That means when we're using a helical gear, there is a push or a pull to the camshaft or whatever we're driving with that gear in a direction that we're not wanting us to have movement. So spur cut gears are probably more common. It's hard to say. I've seen a lot of both helical and spur cut. But again, I encourage you to look more into gear tooth geometry in relation to spur cut gears or helical cut gears. Gear backlash must be measured when assembling the gear train of an engine. What is gear backlash? It is the play between the gear teeth. There needs to be a little bit of play between those gear teeth for it to be as designed by the manufacturer. I can keep going all day long, I think, with any of these subjects we've discussed. Again, I encourage you to look through my PowerPoints. It's kind of hard to keep a lecture going past just the core information that I intended to give you without the interaction of you guys asking questions and that the discussion. The discussion between student and instructor is a huge part of this process. So again, I encourage you all to ask questions. Be on the lookout on Blackboard. I'll probably have the final out shortly after I post this video. Please forgive me for our time schedule here and how I've put out these videos and the corresponding content. We kind of were thrown for a loop there. I really wish we could have continued in person. I think we get more out of it overall when we're in person, but we're doing the best we can here. I think I'm going to end it off here. We've covered the general cylinder head valve train components and general operation of those components. And again, if you guys have any questions, feel free to message me on Blackboard. Get on the discussion page of the Blackboard and let's get in there and have a class discussion. I think, like I said, we learn more. Even when someone else has to ask a question, It may be something a question you didn't even think of that someone else asked, and we can all benefit from that question. So please do that. And may our paths cross again sometime in the future. I'll see you guys later. I hope you have a long, fulfilling career. Thanks.